Hi friends, welcome back to our series of sessions on energy efficiency aspects in industry. Today we shall discuss about electrical systems that are applicable to any plant or industry whenever we are looking at energy conservation point of view. High tension consumers have to pay a maximum demand charge in addition to the usual charge for the number of units consumed. This charge is usually based on the highest amount of power used during some period, say 30 minutes during the metering month. The maximum demand charge often represents a large proportion of the total bill and may be based on only one isolated 30-minute episode of high power use. Considerable savings can be realized by monitoring power use and turning off or reducing non-essential loads during such periods of high power use. Maximum demand controller, on the other hand, is a device designed to meet the need of industries conscious of the value of load management. An alarm is sounded when demand approaches a present preset value. If corrective action is not taken, the controller switches off non-essential loads in a logical sequence. As we are seeing in this figure, this sequence is predetermined by the user and is programmed jointly by the user and the supplier of the device. The plant equipment selected for load management are stopped and restarted as per the desired load profile. The demand control scheme is implemented by using suitable control contactors. Audio and visual annunciations could also be used. Automatic power factor controllers have various types with relay and microprocessor logic. Two of the most common controls are voltage control and kVAR control. Voltage control alone can be used as a source of intelligence when the switched capacitors are applied at a point where the circuit voltage decreases as circuit load increases. Generally, where they are applied, the voltage should decrease as the circuit load increases, and the drop in voltage should be around 4 to 5% with increasing load. Voltage is the most common type of intelligence used in substation applications when maintaining a particular voltage is of prime importance. This type of control is independent of the load cycle. During light load time and low source voltage, this may be a leading power factor at substation, which is to be taken care of. Then we have the kVAR control, also called as kiloVAR sensitive controls, which are used at locations where the voltage level is closely regulated and not available as a control variable. The capacitors can be switched to respond to a decreasing power factor as a result of the change in system loading. This type of control can also be used to avoid a penalty on the low power factor by adding capacitors in steps as the system power factor begins to lag behind the desired value. KVAR control requires two inputs, current and voltage from the incoming feeder, which are fed to the PF correction mechanism, either the microprocessor or the relay. Then we have automatic power factor control relay, which controls the power factor of the installation by giving signals to switch on or switch off of power factor correction in capacitors. Relay is the brain of the control circuit and needs contactors of the appropriate rating for switching on off the capacitors on off. There is a built-in power factor transducer which measures the power factor of the installation and converts it into a DC voltage of the appropriate polarity. This is compared with the reference voltage, which can be set by means of a knob calibrated in terms of the power factor. When the power factor falls below the setting, the capacitors are switched on in sequence. The relays are provided with the first in, first out, or first in, last out sequences. The capacitors controlled by the relay must be of the same rating and they are switched on or off linear sequence. To prevent overcorrection hunting, a deadband is provided. This setting determines the range of phase angle over which the relay does not respond. The relay acts only when the power factor goes beyond this range. When the load is low, the effect of capacitors is more pronounced and may lead to hunting. Under current blocking, which is low current cutout, shuts off the relay, switching off all capacitors one by one in a sequence when the load current is below setting. Special timing sequences ensure that the capacitors are fully discharged before they are switched in. This avoids a dangerous overvoltage transient. The solid state indicating lamps display various functions that the operator should know and also indicate each capacitor switching stage. Then we have the intelligent power factor controller, IPFC. This controller determines the rating of the capacitance connected to at each step during the first hour of its operation and stores them in memory. Based on this measurement, the IPFC switches on the most appropriate steps, thus eliminating the hunting problems normally associated with capacitor switching. Then we have energy efficient motors. Basically, minimizing watt loss in motors. Improvements in motor efficiency can be achieved without compromising motor performance at a higher cost within the limits of existing design and manufacturing technology. It can be seen that any improvement in motor efficiency must result from the reducing the watt losses. In terms of the existing state of electric motor technology, a reduction in watt losses can be achieved in various ways. All these changes to reduce motor losses are possible with the existing motor design and manufacturing technology. They would, however, require additional materials and or use of such high quality materials and improved manufacturing processes, resulting in increased motor cost. Thus, energy efficient electric motors reduce energy losses through an improved design, better material, and improved manufacturing techniques. Replacing a motor may be justifiable solely on the electricity cost savings derived from an energy efficient replacement. This is true if the motor runs continuously as power rates are high. The motor is oversized for the application, or its nominal efficiency has been reduced by damage or previous results. Efficiency comparison for standard and high efficiency motors are seen here. Whereas the standard motor is the energy efficiency motor. Normal efficiency for the same horsepower rating of 10 HP, you have the 90% efficiency for energy efficient motors. Whereas standard motors, it is just over 84%. That's a typical energy efficiency figures that we see. If you see the technical aspects of energy efficient motors, they last longer and may require less maintenance. At lower temperatures, bearing grease lasts longer. The required time between regreasing increases. Lower temperatures translate to long-lasting insulation. Generally, motor life doubles for each 100 degrees centigrade reduction in operating temperature. Select energy-efficient motors with a 1.5 service factor and design for operation at 85% of the rated motor load. Electrical power problems, especially poor incoming power quality, can affect the operation of energy-efficient motors. Speed control is crucial in some applications. In polyphase induction motors, slip is a measure of motor winding losses. The lower the slip, the higher the efficiency. Less slippage in energy-efficient motors results in speeds about 1% faster than in standard counterparts. Starting torque for energy-efficient motors may be lower than for standard motors. Facility managers should be careful when applying efficient motors to high torque applications. Then we have these electronic soft starters. We all know when starting an induction motor, AC induction motor develops more torque than is required at full speed. This stress is transferred to the mechanical transmission system, resulting in excessive wear and the premature failure of chains, belts, gears, mechanical seals, etc. Additionally, rapid acceleration also has a massive impact on electricity supply charges, with high inrush currents drawing 600% of the normal run current. The use of star delta only provides a partial solution to the problem. Should the motor slow down during the transition period, the high peaks can be repeated and even when exceed the direct online current. The soft starter provides a reliable and economical solution to these problems by delivering a controlled release of power to the motor, thereby providing smooth, stepless acceleration and deceleration. The motor life will be extended as the damage to windings, bearings is reduced. Soft start or soft stop are built into three-phase units, providing controlled starting and stopping with a selection of ramp times and current limit settings to suit all applications. We have the current at 600%, direct current, time and speed. And then the mechanical stress, if you see, surge and reduction on with gradual acceleration and reduction, soft start and soft stop applications. The advantages of the soft start can be less mechanical stress, improved power factor, lower maximum demand, and less mechanical maintenance. Then we have the variable speed drives, speed control of induction motors. Induction motor is the workhorse for the industry. It is cheap and rugged and provides high power to weight ratio. On account of high cost implications and limitations of the DC system, induction motors are preferred for variable speed applications, the speed of which can be varied by changing the supply frequency. The speed can also be varied through a number of other means, including varying the input voltage, varying the resistance of rotor circuit, using multi-speed windings, using Scherbus and Kramer drives, using mechanical means such as gears, pulleys, and eddy current or fluid coupling, or by using rotary or static voltage and frequency converters. Then we have variable frequency drive. The VFD operates on a simple principle. The rotational speed of an AC induction motor depends on the number of poles in the stator and the frequency of the applied AC power. Although the number of poles in an induction motor cannot be altered easily, variable speed can be achieved through a variation in the frequency. The VFD rectifies the standard 50-cycle AC line power to DC, then synthesizes the DC to a variable frequency AC output. Motors connected to VFD provide variable speed mechanical output with high efficiency. These devices are capable of up to 9:1 speed reduction ratio, 11% of full speed, and 3:1 speed increase with 300% of full speed. In recent years, the technology of AC variable speed drives, variable frequency drives have evolved into a highly sophisticated digital microprocessor control along with high switching frequency of insulated gate bipolar transistors. This has led to significantly advanced capabilities from the ease of programmability to expanded diagnostics. The two most significant benefits from the evolution in technology have been those of cost and reliability, in addition to the significant reduction in the physical size. Then we have variable torque versus constant torque. Variable speed drives and the loads that are applied to can generally be divided into two groups, constant torque and variable torque. The energy savings potential of variable torque applications is much greater than that of constant torque applications. Constant torque loads include vibrating conveyors, punch presses, rock crushers, machine tools, and other applications where the drive follows a constant variable voltage to frequency ratio. Variable torque loads include loads, centrifugal pumps and fans, which make the majority of HVAC applications. Let's see why variable torque loads offer greater energy savings. In variable torque applications, the torque required varies with the square of the speed and the horsepower required varies with the cube of the speed, resulting in large reduction of horsepower for even a small reduction in speed. The motor will consume only 12.5% as much energy at 50% speed than it will at 100% speed. This is referred as affinity loss, which define the relationship between speed, flow, torque, and horsepower. The following laws illustrate the relationship. Flow is proportional to speed, head is proportional to the square of the speed, torque is proportional to the square of the speed, and power is proportional to the cube of the speed. These are the laws that govern the relations, motor relations. Then we have tighter process control with variable speed drives. No other AC motor control method compares to variable speed drives when it comes to accurate process control. Full voltage starters can only run the motor at full speed, and soft starts and reduced voltage soft starters can only gradually ramp the motor up to full speed and back down to shut down. Variable speed drives, on the other hand, can be programmed to run the motor at a precise speed, to stop at a precise position, or to apply a specific amount of torque. In fact, modern AC variable speed drives are very close to the DC drives in terms of fast torque response and speed accuracy. However, AC motors are much more reliable and affordable than DC motors, making them far more prevalent. Most drives used in the field utilize the volts or heads type control, which means they provide open loop operation. These drives are unable to retrieve feedback from the process, but are sufficient for the majority of the variable speed drive applications. Then we have many open loop variable speed drives do offer slip compensation, through which enables the drive to measure its output current and estimate the difference in actual speed and set point. Then we have extended equipment life and reduced maintenance. Single speed starting methods start motors abruptly, subjecting the motor to a high starting torque and to current surges that are up to 10 times the full load current. Soft starts and reduced voltage soft starter, RVS as we popularly call, are also step a motor up gradually, but drives can be programmed to ramp up the motor much more gradually and smoothly, and can operate the motor at less than full speed to decrease the wear and tear. Variable speed drives can also run a motor in specialized patterns to further minimize mechanical and electrical stress. For example, a S-curve pattern can be applied to a conveyor application for smoother control, which reduces the backlash that can occur when a conveyor is accelerating or retarding. Typical full load efficiencies are 95% at higher. High power units are still more efficient. The efficiency of variable speed drives generally decreases the speed, but since torque requirements also decreases with speed for many variable speed drives applications, the absolute loss is often not very significant. The power factor of a variable speed drive drops drastically with speed, but a low power requirement and absolutely kVAR requirement is low. So the loss is also generally not significant. In a suitable operating environment, frequency controllers are relatively reliable and need little maintenance. As a disadvantage of static converters is the generation of harmonics in the supply, which reduces motor efficiency and reduces motor output. In some cases, it may necessitate using a motor with a higher rating. Then we have eddy current drives. This method employs an eddy current clutch to vary the output speed. The clutch consists of a primary member coupled to the shaft of the motor and a freely revolving secondary member coupled to the load shaft. The secondary member is separately excited using a DC field winding. The motor starts with the load at rest, and a DC excitation is provided to the secondary member, which induces eddy currents in the primary member. The interaction of the fluxes produced by the two currents gives rise to a torque at the load shaft. By varying DC excitation, the output speed can be varied to match the load requirements. The major disadvantage of the system is the relatively poor efficiency, particularly at low load applications. Then slip power recovery system is more efficient alternatives to speed control mechanism for use with slip ring motors. In essence, a slip power recovery system varies the rotor voltage to control speed, but instead of dissipating power through resistors, the excess power is controlled from slip rings and returned as mechanical power to the shaft or as electrical power back to the supply line. Because of the relatively sophisticated equipment needed, slip power recovery tends to be economical only in relatively high power applications and where the motor speed ranges 1:5 or less. Then we have the fluid coupling, which is one way of applying varying speeds to the driven equipment without changing the speed of the motor. We see the construction of the fluid coupling. They work on the hydrodynamic principle. Inside every fluid coupling are two basic elements, the impeller and the runner, and together they constitute the working circuit. One can imagine the impeller as a centrifugal pump and the runner as a turbine. The impeller and the rotor are bowl-shaped and have a large number of radial vanes. They are suitably enclosed in a casing, facing each other with an air gap. The impeller is connected to the prime mover, while the rotor has a shaft bolted to it. This shaft is further connected to the driven equipment through a suitable arrangement. Thin mineral oil of low viscosity and good lubricating qualities is filled in the fluid coupling from the filling plug provided on its body. A fusible plug is provided on the fluid coupling, which blows off and drains out oil from the coupling in case sustained overloading. The energy efficient transformers. We have most energy loss in the dry type of transformers occurs through heat or vibration from the core. The new high efficiency transformers minimize these losses. The conventional transformer is made up of silicon alloyed iron core. The iron loss of any transformer depends on the type of core used in the transformer. However, the latest technology is to use amorphous material, a material glass alloy for the core. The expected reduction in energy loss over conventional silicon iron core transformer is roughly 70%, which is quite significant. By using an amorphous core with unique physical and magnetic properties, these new types of transformers have increased efficiencies even at lower loads, say 98.5% efficiency at 35% load. Electrical distribution transformers made with amorphous metal cores provide excellent opportunity to conserve energy right from the installation. Though these transformers are a little costlier than conventional iron core transformers, the overall benefit towards energy savings compensate for the higher initial investment. At present, amorphous metal core transformers are available up to 1600 kVA. If you see the fluid coupling operating principle, there is no mechanical interconnection between the impeller and the rotor, and power is transmitted by the value of the fluid filled in the coupling. When the impeller is rotated by the prime mover, the fluid flows out radially and then axially under the action of centrifugal force. It then crosses the air gap and runner is directed towards the bowl axis back to the impeller. To enable the fluid to flow from the impeller to the rotor, it is essential that there is a difference in the head between the two, and thus it is essential that there is a difference in RPM known as slip between the two. Slip is an important and inherent characteristic of a fluid coupling, resulting in several desired advantages. As the slip increases, more and more fluid can be transferred. However, when the rotor is at standstill, the maximum fluid is transmitted from the impeller to the rotor, and the maximum torque is transmitted from the coupling. The maximum limiting torque, the fluid coupling also acts as torque limiter. If we see the characteristics of fluid coupling, has a centrifugal characteristics during starting, thus enabling no load or startup the prime mover, which is of great importance. The slipping characteristics of the fluid coupling provides a wide range of choice of power transmission characteristics. By varying the quantity of oil filled in the fluid coupling, the normal torque transmitting capacity can be varied. The maximum torque or limiting torque of the fluid coupling can also be set to be predetermined safe value by adjusting oil filling. The fluid coupling has the same characteristics in both directions of rotation. Then we have the famous electronic ballast. If you see the role of ballast in an electric circuit, the ballast acts as a stabilizer. The fluorescent lamp is an electric discharge lamp. The two electrodes are separated inside a tube with no apparent connection between them. When sufficient voltage is impressed on these electrodes, electrons are driven from one electrode and attracted to the other. Current flow takes place through an atmosphere of low pressure mercury vapor. Since the fluorescent lamps cannot produce light by direct connection to the power source, they need an ancillary circuit and device to get started and remain illuminated. The auxiliary circuit housed in a casing is known as the ballast. If you see the conventional versus electric ballast, conventional ballasts make use of the kick used by a sudden physical disruption of the current in an inductive circuit to produce the high voltage required for starting the lamp, and then rely on a reactive voltage drop in the ballast to reduce the voltage applied across the lamp. On account of the mechanical switch, which is a starter, and low resistance of the filament when cold, the uncontrolled filament current generally tends to go beyond the limits specified by Indian standards specifications. With high values of current and flux densities, the operational losses and temperature rise are on the rise. higher side in the conventional choke. The high frequency ballast overcomes the above drawbacks. The basic functions of electronic ballasts are to ignite the lamp, to stabilize the gas discharge, and to supply power to the lamp. The electronic ballasts, as we are seeing in the figures, make use of modern power semiconductor devices for their operation.